Okay, so today we are going to use this handy dandy technique called linearizing, which will oftentimes make data easier to interpret. This technique is used frequently in physics and it's used frequently in other sciences and mathematical courses as well. So let's say we have two different sets of data. Let's say one set of data, it looks kind of like that. Oh, excuse me. And then the other set of data looks kind of like this. Cool. So looking at these right off the bat, which set of data looks easier to interpret? Honestly, one on the left looks a lot easier. This data is pretty darn linear overall, and linear data is just easier to interpret, just because the slope is always going to be a rate of something. Who knows what that rate is? We'll do a couple of different examples in a second. And then the intercept will either be like some zero value or represent some non-zero important point. Great. So if you have a set of data that isn't linear, you can do two things. You can either leave it as a model that is nonlinear, or you can transform the data so that it is linear. And if you choose to transform the data to make it linear, you are using this technique called linearizing. Great. So today we're going to go ahead and use the linearizing technique to experimentally determine the value for a pi. Cool. So what I went ahead and did is I found how many different objects? 7 different objects. And I measured the radius of those objects in centimeters. And then I went ahead and I measured the area of each of those objects just using graph paper and my ruler. So it was a little bit tedious, but I got it eventually. And again, I did not use any calculations to find the area of these circular objects. I just went ahead and used measuring. Great. Even though I know in the back of my head, I know what the area of is a circle, but I pretended I knew nothing. Great. So I went ahead and took all the data, and then what I did is I made a graph of it, of the area of its radius of a circle. Cool. So that's our first step. Great. So now looking at my data, we're going to go to step number 2, which is looking at the shape of the type of relationship it represents for our data. So if we look at our data, this data right here for my graph, it looks, honestly, pretty darn quadratic. Yeah, that looks very quadratic to me. Great. And honestly, I know in my head that it should be quadratic too, so I'm using some of my known knowledge as well. Okay, so now what we're going to do is we're going to combine steps 2 and 3. So we said the relationship between the radius and area of a circle looks like it's quadratic. So I know in my head that it should be area of a circle is pi r squared. I know that's what it should be. What I'm going to do is we want to go ahead and linearize our data. So we know that the equation for a linear equation is y equals mx plus b. Okay, so if we look at our data, we know that like the dependent variable is the area. So the area is like, in this case, our y variable, our dependent variable on the y-axis. Great. So to make this data linear, we are going to have the radius. So radius was just regular old radius. Radius is like the independent variable. We need to graph radius squared. And I think of it as like radius squared is like x. And then, if we look at this, b in this case, b looks like it's just plus 0. So let's highlight that. So b is 0 in this case. So then that leaves us the pi value is going to be m, or the slope. So the slope in this case will likely be pi. So we're going to go ahead and linearize our data. So for step number 3, I have on the left-hand side the radius and then the corresponding area that I measured. Now what we're going to do is we're going to go ahead and linearize that. So in this case, the area is just the y value. So I'm just going to put area is the same. That's centimeters squared for each thing. But the x value is going to be the radius squared. So I'm going to need to take each of my radiuses and square it. So I'm going to put this is radius squared. So that's going to be centimeters squared. Okay. So radius squared. So 2 squared is 4. And then the area is still 13. That is staying the same. The radius squared, 6 squared is 36. Area is still 110. 7 squared is 49. 145, and so on and so on. What, 144 and 450. Okay, and we have what? 13 squared, 169, 525 is still that. Now 16 squared was that, 256, and then this is still 830. Perfect. So now we have our data. This right here on the right-hand side, this is our linearized data. And again, it's because we're using the equation comparing it to a linear form, y equals mx plus b, and we knew what the relationship should likely be like. Cool. So now let's go ahead and go on to step number 4. Cool. So step number 4 is create a graph of the new data. So our new data was radius squared for the independent variable on the x-axis and area on the y-axis. Cool. We look at this data. Oh my goodness, that is so cool. That looks pretty darn linear. If we want to draw a best fit line, and again, always use a straight edge or a ruler to do it, or you can do it on a computer if you have a computer. But make sure you have about the same number of points above and below your best fit line. Or if your data is really pretty darn good, they'll probably all touch that best fit line, but that's pretty rare. Great. And cool. So now let's go on to step number 5. Okay. So now for step number 5, I used the slope-intercept form, so y equals mx plus b, to create exact relationship for your data. So I just went ahead and did that in Excel. And I got Excel to tell me that the y is 3.263 times x minus 6.07. Our squared value is almost 1, so that's pretty darn good. Cool. So let me just write this out. So we know y equals what? Mx plus b. In this case, that relationship was 3.2263x minus 6.07. And again, the y variable is the area, so 3.2263. And then the x variable is radius squared minus whatever our y-intercept was. Cool. So again, let's compare this to our linear equation. So y equals mx plus b. So we know our b value in this case was negative 6.07. So not exactly what we wanted. 0 is really what it should be, but that's pretty darn close to 0. The area is our y variable. R squared is our x variable. And our slope is 3.263. So we know our general form for a circle is area equals pi r squared. Let me just go down and rewrite all this stuff, highlight it the same color. Cool. So in this case, it looks like the slope is 3.2263, which is m, which is pi in this case. So in this case, the slope is 3.2263, which is pi. And pretty cool thing is, the pi value should be 3.1415, et cetera, et cetera. 3.22, that's pretty darn close. Like there's always going to be a little bit of error in all of our data. Cool. And so we were doing right there, we were using the equation of the best fit line from our linearized data to find out useful information. So I just added a little step number 6 at the end, but we're always going to use that best fit line to find some good information.